Good day, everyone. I am here to make a presentation on the topic Physico-chemical characterization of date palm seed as a reinforcement in aluminium matrix composite. This paper is written by Thomas Oradakwe, Oluwasegun Ajide, and Adekunle Adeleke. I am the presenter, Thomas Oradakwe. Aluminium alloy is known for its lightweight and good metallic properties, which has made it to be used in many engineering applications. Aluminium is often reinforced with secondary materials, including agro waste, to improve its properties. Date seed, on the other hand, is known for its remarkable properties such as corrosion inhibition and high bonding strength in brick production. However, aluminum alloy has some limitations, including poor durability, low thermal expansion, low strength. These defects affect the service property of the alloy. We can see from figure 1 that there are cracks in fabricated aluminum components, and in figure 2 we are seeing the same graph showing pores in fabricated aluminum alloy by casting. Secondary reinforcement can improve these defects, and the use of agro waste has gained predominance in research. However, the use of date palm seed as a reinforcement aluminum matrix has not been investigated. In this wise, we hope to conduct a Fourier transform infrared analysis, X-ray fluorescence analysis to investigate the functional groups and the oxides present in date palm seed samples, and do a comparison with similar studies on agro waste reinforced aluminum composites. The research method involve the use of Fourier transform infrared spectroscopy and X-ray fluorescence spectroscopy. The Agilent Carry ZNSC FTIR analyzer was used for the FTIR tests, while thermoofficial dispersive XRF analyzer was used for the XRF analysis. FTIR analysis shows us the functional group present in the sample, while the XRF analysis determines the elements and the oxide composition of the samples. The samples were prepared by crushing. The non-ash was only crushed and then mixed with 1 milligram of potassium bromide at 200 milligrams. The mixed powders were put in the hydraulic press. Thereafter, the FTIR machine was degassed with nitrogen, and then the samples were exposed to infrared radiation at 400 to 4,000 per centimeter wavelength. The graph of transmitters against wave number was plotted electronically. For the XRF analysis, samples were turned to chips, binder were mixed with the chips and ground, and the samples were then pressed into briquettes using a die press. Briquettes were placed in XRF analyzer. Quantitative and qualitative analysis were performed. The ash sample were prepared by calcination of the crushed non-ash date palm seed in an electric mobile furnace at about 500 degrees Celsius. The FTIR results show that for the non-ash, that the functional group present include hydroxyl, a key component of phenol. According to Benjamin et al., date palm seed has phenol, and this has been extracted in corrosion inhibition studies. Now, it is important to see the direct usage of date palm seed as a reinforcement and how this will affect the corrosion properties of the composite. Meanwhile, for the non-ash, only Akin was present in the FTIR analysis, which collaborates with Adeleke's finding in 2021 that showed that calcination of biomass express key functional groups. It will be very interesting to see the behavioral difference in terms of corrosion resistance of the non-ash date seed reinforced aluminum composite and the ash date seed reinforced aluminum composite. XRF analysis, the qualitative XRF analysis shows the minerals present in the date palm seed sample. For the non-ash, we could see iron, silver, potassium, copper, manganese, all having spikes. The intensity of the elements are indication of their relative abundance according to Barrow method 2018. In the ash sample, there are many There are more elements, but these elements are at lower intensity. Of course, potassium was still the most predominant, followed by iron, and then calcium, then zinc. The quantitative analysis showed that sodium oxide, magnesium oxide, titanium oxide, iron oxide, calcium oxide, potassium oxide, chromium oxide, manganese, aluminum oxide, and so forth were present in both non-ash and ash samples. Magnesium was the most predominant oxide in the non-ash sample, while potassium oxide was the most predominant oxide in the ash sample. Comparing this with that of other studies, similar oxides are present in other agro wastes that have been used in fabricating or synthesizing aluminium composites. Key findings from this study includes that the oxide in date palm seed ash and non-ash are similar to those of coconut shell ash, carbon ash, groundnut shell ash, palm kernel shell ash, and rice husk ash. The date palm seed samples present a novel reinforcement potential due to the prevalence of magnesium oxide in the non-ash and potassium oxide in the ash samples. The presence of phenol in the non-ash sample shows its potential to inhibit corrosion, which could impact the corrosion behavior of the composites. In conclusion, preliminary qualification of date palm seed showed the presence of similar oxides present in other that have been used as reinforcement materials in aluminium composites. The major oxide in the raw date palm seed is magnesium oxide, about 68%, while that of the ash is potassium oxide, about 43%. This suggests that using palm seed and date palm seed ash as reinforcement may introduce some new properties in aluminium composites. The FTIR result also showed the potential of date palm seed impacting the corrosion behavior of aluminium composites. This study can be verified and confirmed by synthesizing the date palm seeds reinforced aluminium composites. Meanwhile, researchers can begin to investigate the use of raw agro waste and not only agro waste ash in the synthesis of composites. Thank you.